Hey guys, it's Professor Floyd here, and we are going to talk about Henry's Law today. So, as you can see, Henry's Law is a relationship, it's a concept that describes the ratio of the concentration of some substance in a solution that's been dissolved into that solution versus the concentration in the gas phase. So we might think of dissolved oxygen. So the concentration of O2 that's aqueous divided by the concentration O2 that's in the gas phase. So of course the concentration of O2 is roughly 18 or 19%, 19% of our atmosphere. And then our atmosphere is 760 torr. So we oftentimes express the concentration of the gas as a pressure instead of actually a concentration. And from that, the Henry's Law constants are usually expressed in moles per liter per pressure unit. Oftentimes it might be millimeters of mercury, and of course millimeters of mercury is the same thing as torr, but sometimes it's also expressed as bar. So just depending on where you get your constant values from will depend on what the units of your Henry's Law constant are. It really doesn't matter because you can use a little bit of dimensional analysis to manipulate those constants and go from bar to torr or to kPa or whatever it is that you'd like. And instead of expressing it as moles, you could multiply by the molecular weight and you could express it as grams of the particular substance. So we also know that CO2 has some environmental concentration around 400 ppm, and we can express that as a partial pressure, and we can calculate what our dissolved CO2 concentration would be in, say, the oceans, because maybe we're concerned about global warming, climate change, more CO2 in the atmosphere, which means that more CO2 will dissolve into our oceans. And that one we would be concerned about because CO2 will form an equilibrium with carbonate and form carbonic acid. So it causes ocean acidification, right? So that's something that's been in the news in the past 10 to 15 years, in the 2000s and more recently. So what we're going to talk about today, though, is applying this to environmental science, environmental health, and industrial hygiene. So Henry's Law is a really good way for us to predict the concentration of a solution, the concentration of a contaminant like toluene that generally is not very soluble in water. It's a volatile, so it prefers to evaporate. But if we, say, have a drum, a 30-gallon drum, with 15 gallons water, and somebody adds 40 mils of toluene, then if we wanted to know what will the concentration of toluene be in the headspace, and what will the pressure be in the equilibrium. So of course, if we ask that question, we have two unknowns. We have the unknown concentration and the unknown pressure, and I'll show you how we get around that issue here in just a second. So the first thing we need to do is we need to look up the Henry's Law constant for toluene, and we also need to specify what temperature and pressure we're operating at. So in this case, let's just operate at 25 C, a typical nice, cool fall, autumn day, and we'll say that we're on a loading dock somewhere. So we're at sea level. So we'll call that 25 C and 1 atmosphere. And 25 C, of course, is also 298 Kelvin, just keep that in mind. I don't know that we're going to need it for sure. So our Henry's Law constant, I looked it up a little bit earlier, and it's 0.15. And then our units on this came from the NIST. So they like to express the units in moles per kilogram bar. Okay, so we can convert this right away because we know that a kilogram of water is equal to a liter of water. So if we simply multiply our 0.15 moles per kilogram bar by the density of water, 1 kilogram mass per volume is density per liter, we're now in moles per liter bar. So we could go ahead and change this, but let's just wait because we don't necessarily know what units we're going to end up in. And so we can do that as we do our math. So we'll just call this moles per liter bar. Now, if this had been, so this is the Henry's Law constant at a temperature and for toluene into water. That would be different if it was toluene into isopropyl alcohol, toluene into vegetable oil, toluene into something else. So it's specific to the substance that it's dissolving into and the temperature at which it's dissolving. So now our particular problem, we want to know what's going to be the concentration in the headspace, what's going to be the concentration in the liquid. So the first thing we should ask ourselves is, can it all dissolve? So we should calculate what's the maximum solubility. Well, to do that, we have to calculate what's the maximum concentration in the air. So the maximum concentration in the air is going to come from the vapor pressure of toluene. So the vapor pressure of vapor toluene is going to come from we can calculate it from the Antoine equation. I'm not going to do that right now. I'm going to provide it for us. I've calculated that already. And if you don't remember the Antoine equation, I suggest you look it up. NIST has, it's not very complicated, and NIST webbook has constants that you can use that have been experimentally determined and empirically verified through experiments. And they have a nice listing of that. So in these conditions, it's 28.45 torr. So 28.45 torr is the maximum pressure, it's the pressure that will be exerted by toluene in equilibrium with itself. So this is its vapor pressure. This is also the pressure that will go into our calculation for concentration of toluene in the aqueous phase is going to be equal to Henry's Law constant multiplied by this pressure from the gas phase. So our pressure from the gas phase, of course, is going to be 28.45 torr. Our Henry's Law is going to be 0.15. And like I said, that's mole per liter bar. Torr and bar don't cancel, so we need to convert our torr into bar. So 1 bar equals 750 torr. So now our torrs cancel, our bars cancel, and we're left in moles per liter. So if we calculate that, that's interesting, but generally we like to express our concentrations for aqueous phase in the environmental world as milligrams per liter because we also call that ppm. So let's go one more step. Let's get out of our moles and let's get into mass units. So we're going to do that with our molecular weight, 92.14 grams per mole. So that takes care of our moles. And then let's get out of grams and into milligrams so we can have a ppm expression. So 1,000 milligrams per gram. Alright, so now this equals 0.15 times 28.45 times 92.14 times 1,000 divided by 7 50, and our final units are going to be milligrams per liter. Alright, so what is this value? This is our concentration in the aqueous phase. So we type that in, 0.15 times 28.45 times molecular weight times 1,000 to get into milligrams divided by 750 to get it into torr, and we have 524.3. 524 milligrams per liter. Alright, that's nice, that's our concentration. We should also calculate what this concentration is and go ahead and express it in milligrams per liter. So we can calculate concentration from pressure, like I was referring to earlier, and like we've done in previous posts, simply by dividing by our atmospheric pressure, 760 torr, and now we've got it expressed in dimensionless units, which is perfect for parts per million. So if we multiply by a million, then that puts us into parts per million. And we get 28.45 divided by 760. That doesn't seem right. There we go. And times a million. So 37,434. We'll just say 37,400. So we can convert from parts per million into milligrams per cubic meter, which is a pretty standard industrial hygiene calculation, by multiplying by our molecular weight and dividing by molar volume. So if we take 37.4 ppm multiplied by 92.14 grams per mole, and then divide by molar volume. So now, if you don't know the molar volume at 25 C in 1 atmosphere, you should calculate it using the ideal gas law. That should be one that you probably got memorized by now. It's 24.45. We're not going to cover that in this post. There's other posts that cover the more basic calculations like that. So 24.45 is the volume. That's liters per mole. The volume that 1 mole of ideal gas will occupy. We're assuming ideality. And so this gives us milligrams per cubic meter. The units cancel out, and so if we were to convert the grams into milligrams, the liters into cubic meters, we'd find that that offsets by a factor of 1,000,000, which takes care of our parts per million. That 10 to the minus 6 is implied right there. So we take this number, multiply by 92.14, divide by, and this comes out to 1.41 times 10 to the 5th milligrams per cubic meter. So that's a lot. That's a high concentration, but we want it in milligrams per liter. So divide by 1 cubic meter per 1,000 liters. So just divide this by 1,000. That's 1.41 times 10 to the third. I'm sorry, 10 to the second. Take 3 away. 10 to the second, which is the same thing as 141 milligrams per liter. All right, so our concentration in the air is 141 milligrams per liter. So now we ask the question, does it all dissolve? So the mass in air, or in the headspace, is going to be equal to the concentration in the headspace, 141 milligrams per liter, multiplied by the volume of the headspace. So we're assuming this 30-gallon drum holds exactly 30 gallons. We have 15 gallons of water, which means we have 15 gallons of air. So times 15 gallons times 3.78 liters per gallon. So our liters then cancel, and we're just left with mass units. And so what does that come out to? 141 times 15 times 3.78. So that comes out to 7,995 milligrams, which is also basically equal to 1, 2, 3 grams, 8 grams, right? So we have 8 grams in our air, and then the mass in the aqueous phase is going to equal the same thing. The concentration in the aqueous phase, 524 milligrams per liter, multiplied by the same volume, so times 15 gallons times 3.78 liters per gallon. And so this is going to equal something like 524 times 15 times 3.78. 29,710 milligrams, which of course, 1, 2, 3, is 29.7 grams. All right, so our total mass, if this was at saturation, would be 8 milligrams from the air and 29.7, sorry, that's just 8 grams from the air, 29.7 grams from the water, which equals plus 8, that's not right, 29.7 plus 8, I should just do that in my head, but it's 37.7 grams. Okay. So that would be at saturation. But how much did we input? We input 40 mils, and if the density of toluene is 0.87, then we have 40 mils times 0.87 grams per mil, which equals 34.8 grams. So we have 34.8 grams of toluene added to the system, but if it's at equilibrium, it would be 37.7 grams. So that is no bueno, and that tells us we are not at saturation. So now we've got to solve this from the standpoint of, okay, let's use our Henry's law and let's calculate this. The way we do this, since we have two unknowns in the Henry's law of what our concentration in the aqueous phase is compared to our concentration in the vapor phase, is we look at it in terms of mass because we have a known mass. And we express one concentration in terms of the other. So, we have our concentration aqueous equals 524 milligrams per liter. Our concentration air equals 141 milligrams per liter. All right, now that's down. We can say, we can observe something that is true to Henry's law, that we have already calculated what a real concentration is in the aqueous phase at a real pressure. And that particular example that we calculated is at saturation. But we don't have to do that at saturation only. That doesn't hold true for only saturation. It holds true for any vapor pressure, or vice versa. So any level of saturation is going to provide this ratio. So if we let X equal the concentration in the air, which we know equals 141 milligrams per liter, then the concentration in the aqueous phase, which is equal to 524 milligrams per liter, equals some multiple of x. And the multiple of x is 141 over 524. So we calculate that. Sorry, it's not. It's 524 over 141 because this is numerous times larger than air. So 524 divided by 141 it would help if I punched the numbers incorrectly. Is 3.716 x. So now everything's expressed in terms of x. And we know that we input a certain mass of 34.8 grams. And that is going to partition into the vapor phase and into the aqueous phase with none left behind as a pure substance. No liquid toluene will be left behind. It will all evaporate or dissolve into the water. And it's going to do so according to this relationship. So in the air, we will have X concentration, but we're looking for mass, so we multiply that by our volume. So remember, this is milligrams per liter, so we'll multiply that by our 56.7 liters, same thing as 15 gallons, in the air, and add that to the mass that's in the aqueous phase, which is 3.716 x multiplied by 56.7 liters. So we have this unified expression in terms of mass. We have 56.7 x liters plus 210.7 x liters. So that comes out to 267.4 x liters. And so our 34.8 grams equals, if we divide out both sides by 267.4 liters, then we'll be left with just x, right? So 267.4 liters, and then we'll be in grams per liters unit. So that's concentration units, which is true. That's what we had here originally. Now we said let x equal the concentration in air, and here we have it expressed in milligrams. That's not going to affect anything. But if you're upset about that, then you can go ahead and convert your grams into milligrams. So it'll work out into the right units initially. But let's just do that real quick. Divided by 34.8 inverse. All right. So this equals 0.130 grams per liter, or 130 milligrams per liter. Just multiply it by 1,000. So that's our concentration of X, which is our concentration in the air. So we took it at saturation, it was this value, but we're not at saturation. So at our value that is near to saturation, we find that the concentration, so this is sat, but our concentration in the air is equal to 130 milligrams per liter. Our concentration aqueous is equal to 3.716 times that, 487. 484 milligrams per liter. All right, and so that's how we solve it. This will be our answer. What is the concentration in the air? What's the concentration in the water? It's 130 milligrams per liter in the air, 484 milligrams per liter in the water. I hope that helps. Give me your input and let me know if you catch any mistakes or typos.